Until the middle of the 20th century, scientists like Einstein, Chandrasekhar and Schwarzschild calculated the structure and predicted the fate of stars with just pen and paper. One can then wonder, why do we need computers to understand stars and the universe? We can learn a lot about the universe with astronomical telescopes, such as the European Very Large Telescope and soon with the Extremely Large Telescope. To understand the evolution of the universe, however, we need to complement astronomical observations with theory. Indeed, stars and the universe evolve over millions to billions of years, so we can only take snapshots of the universe with observations of stars and galaxies. The ever-increasing computing power enables us to calculate more and more detailed theoretical simulations of the evolution of the universe, galaxies, stars and planets. For example, cosmological simulations are able to recreate the evolution of the universe at the largest scales from only millions of years after the Big Bang until billions of years later. As part of international research projects like the CATEC Cost Action, scientists then compare theoretical models to observations of stars and galaxies to understand how the universe works. Computer simulations of stars enable us to study the interactions between nuclear reactions and turbulent flows in the deep interior of stars. In previous Astronuclear Nibbles, you already learned about nuclear reactions, how we can use nuclear physics experiment to determine how fast they proceed and how they power the Sun. The Sun and other stars are complex objects in which a wide range of physical processes occur, like turbulence. The turbulent flow of the hot gas inside stars, called plasma, is chaotic, much like the flow of air behind a lorry. Ideally, one would model stars and their evolution with three-dimensional simulations. Despite the great computing power available nowadays, this is unfortunately not possible. Indeed, stars live for millions to billions of years, whereas the physical processes taking place in them have much shorter timescales. For example, the turbulent transport of energy has a timescale of days at most. We thus need to compromise and use a combination of detailed three-dimensional simulations and more general theoretical models, making reasonable assumptions like spherical symmetry. This is a good approximation since stars, like wasabi peas, are quite spherical. This makes the more general models one-dimensional, or 1D for short, meaning that quantities like temperature only depend on a distance from the center of the star. Such 1D models allow us to simulate the entire evolution of stars on a laptop in about a day. Detailed 3D simulations are used to check and improve the assumptions made in the 1D models. One example of 3D simulations of stars is that of neon burning in massive stars. You can see the part of the star that the simulation recreates in this image. We call this approach box in a star simulation. These simulations allow us to study in detail how turbulent flows interact with nuclear reactions. In this movie, you can see this interaction for several nuclides: oxygen on the top left, neon on the top right, magnesium on the bottom left, and silicon on the bottom right. Even though we only simulate the flow inside a small fraction of the stars for a little while, about 1 hour of the star's life in the case of these neon burning simulations, such simulations take months to calculate on supercomputers like the Mare Nostrum 4 supercomputer in Barcelona. These supercomputers have the computing power of thousands of laptops. And being inside of a church, the calculations are even supervised by the Almighty. It is interesting to compare the computing time it takes for general 1D and detailed 3D simulations. For a 1D general simulation, it takes roughly 1 day on a laptop to simulate millions or more years of the evolution of stars. Whereas for a 3D simulation, it takes more than 30 days on the equivalent of thousands of laptops to simulate an hour of just 10% of a star. 3D simulations are thus a lot more expensive than 1D models. More than 1,000,000 billion times more expensive. 3D and 1D models of stars can be combined to determine the fate of massive stars. which are stars more massive than about 10 times the mass of the Sun. As you learned in the first Astronuclear Nibble, the Sun and other stars spend most of their life burning hydrogen into helium. Then massive stars carry on to burn helium into carbon and oxygen, then carbon into neon, neon into oxygen and magnesium, and then oxygen and magnesium into elements like silicon and sulfur. Finally, these elements are converted into elements like iron and nickel. Nuclei with masses close to that of iron are the most stable nuclei, which means that nuclear reactions can no longer stop the unavoidable gravitational collapse of the core of massive stars. When the core of massive stars reaches nuclear densities, additionally infalling matter bounces back on the stiff inner core, triggering a shock wave. This shock wave tries to eject the rest of the star. If successful, the shock wave produces a powerful supernova explosion, not too different from the explosion in your mouth when you crunch into a wasabi pea. Massive stars generally produce a neutron star if the explosion is successful and a black hole if it's unsuccessful. Some neutron stars later merge and produce elements like gold, as discussed in the previous episode of Astronuclear Nibbles. The merger of black holes hardly leaves any trace, except very tiny ripples in the fabric of space-time itself. Gravitational wave detectors like LIGO and Virgo are now able to detect these tiny ripples. Stars like the Sun, on the other hand, will leave behind a white dwarf. You will learn more about these exotic objects and other topics in the next episodes of Astronuclear Nibbles. I hope you enjoyed our nibbles as much as we do.